So good morning, everyone. This is Mrs. Price, and I am going to be with you for Chapter 6. The first day, we are going to do 2 lessons in one day, but I'll still try to keep the video as close to 20 minutes or less as possible. And then after that, we'll just do 1 section a day. So we are jumping in with a unit that is on polynomials and then rational functions. We're going to talk in Chapter 6 about 2 different types of functions. So the first several lessons will be on polynomials, and then the next several lessons will be on rational functions. Let's get started. All right, so if we take a look at this table here, there might be some polynomials that you are already familiar with. This first one right here, whenever we just see a letter C, C in math normally represents the word constant. So here we don't have any variable, we just have a constant. So our degree, so the degree is the highest exponent on the x. Since there is no x here, we could think of it as kind of like a constant times, there we go, times x to the 0. And so because of that, our degree is 0. How many terms? Terms are separated by plus or minus signs. So each of these things I'm pointing to would be a term. This has only one term. There's no pluses or minuses in this expression, so it has one term. The degree is 0, and we would call this kind of function a constant function. Our next polynomial, which you might recognize, it's linear. This first one was linear too, it's just that it's a horizontal line. This next one is linear. It has a constant slope of k, and even though you don't see an exponent, we all know there's an invisible 1 on this x. So there's only one term, number of terms is 1, degree is 1, and this function is linear. Next function is also linear, except now we have 2 terms because we have this term and this term. 2 terms separated by a plus sign. Our degree is the highest exponent on the x, which is still just 1, which makes the function still linear. The type of function is based usually on the degree, unless you want to go and get into numbers of terms. We could call this first one a linear monomial, and we could call this one a linear binomial because it has 2 terms. And then, of course, this next one could be a trinomial, but we're going to get more into just based on degree than on number of terms. So here we have a trinomial, 3 terms, so 3 terms. Our degree, our highest exponent is 2. And so when we have a polynomial of degree 2, we call it quadratic. Next one, we have 4 terms. The highest exponent is 3, so the degree is 3, and we call this function cubic. The last one, we have 1, 2, 3, 4, 5 terms. The degree, this highest exponent, is 4, and we would call this function quartic. If we had a 5th degree, it'd be quintic, and so forth. All right, so I think you kind of get the idea of what a polynomial is. A polynomial is really just a sum of a bunch of terms of numbers times x's raised to powers. These numbers are called coefficients, so all these numbers that are in front of the x's, those are called your coefficients, and the coefficients have to be real numbers. No imaginary coefficients, only real numbers for our coefficients. Now our x's are all raised to powers. They can just be an x to the 0, like this guy right here. That would be a number times x to the 0. So 0 is okay, but we cannot have any negative powers. So no x to the -4th, no x to the -10th, no negative powers. The other thing we can't have is we can't have rational exponents, no fractions. So no x to the 1/2, no x to the 2/3. So the exponents must be non-negative. Non-negative means positive or 0, and they must be integers. So we have some examples down here. Oh, and don't forget the degree The degree is the power that has the greatest exponent. It's your highest exponent on a variable for your polynomial. All right, so we just did a very similar table on the previous screen. A constant function just has a number in it. A linear function, constant is a type of linear, but that's okay. A linear function traditionally has an x to the first, and then maybe a constant after it. So like y equals 5x minus 7. Quadratic would be a degree of 2 or an x squared, cubic degree of 3 or an x cubed, and quartic degree of 4 or an x to the fourth. We don't have to have, we don't have to have all of these terms. So for example, I could have a quartic function, an x to the fourth, with no other terms, and it would still be quartic. As long as you have number times x to the fourth, then your degree is 4. Degree is 4. And because of that, it is still quartic even if there are no other terms. So for our example, we have an x to the fourth plus 2x minus 1. There's no x cubed term, there's no x squared term, and that's okay. That's still a quartic function. All right, so we're going to take a look at these examples and decide this is supposed to be connected. I'm just going to kind of like draw these. It's hard to do square roots in this software. So, okay. So we're going to decide if each of these functions is a polynomial or not. Remember, what stops something from being a polynomial? If your x has a negative exponent or a rational some sort of an exponent that's a fraction that's not an integer, if the exponent is a variable, all of those things would cause a function to not be a polynomial. It could still be a function, it just wouldn't be a polynomial function. So we're just going to say yes or no. So for this first one, we have x to the fourth plus pi x cubed minus 5x squared plus 1. Is the pi a real number? Absolutely. Pi is a real number. It's not rational, but it's real. So we are good here. So yes, this is a polynomial. What type of polynomial is it? It is a quartic because the degree is 4. All right, this one, it looks nice, except we have a problem. Does everyone see the problem? We have an exponent that's negative, which means whenever you have a negative exponent, this is not a polynomial. All right, this next one, 4x cubed minus 2x squared minus root 3x. The x is not under the root. If the x was under the root, we'd have a problem. But since the x is not under the root, it's just over the 3, we are good. So because root 3 is still a real number, not rational, that's okay, it's real. So yes, and this would be a cubic function because the degree is 3. This one looks okay. This guy looks okay. Uh-oh, we have a problem right here. When we have a variable in the exponent, if the exponent is a variable, it is not a polynomial. 3 to the x is an exponential function, so this would not be a polynomial. Last one, x cubed is fine, negative 2x is fine, 6 is fine, but uh-oh, this right here, square root of x, is the same thing as x to the 1/2 power. And because of that, we can't have fraction exponents, and therefore, no, this is not a polynomial. All right, so we're going to talk about a concept called differences. So finite differences within the terms of a polynomial. If you take your x's and evenly space them out, in this case, we're just moving by ones. So we're adding 1 each time to get from one x to the next. And then if you take your y's and subtract each pair of subsequent terms. So if we do 13 minus 10, 13 minus 10, we get 3. 16 minus 13, we get 3. 19 minus 16. 22 minus 9, 25 minus 22. If these differences are all the same, that makes this function a first degree function, and we know that it's linear. These differences are another way of saying your slope. So we would have for each change of 1 in our x value, our y value changes by 3. Since our slope is constant, the numbers are all the same. Since our slope is constant, we have a first degree function. And technically, since our y changes by 3 for every x change of 1, our slope is a constant of 3. So, and if we graph the data, the function looks linear. Now, it might not look like the slope is 3, but it is. It's just that the scale is different for the x's and the y's. That's why it kind of looks a little bit shallow, but that's okay. So if we have a constant slope, meaning if you evenly space the x's and subtract each consecutive pair of y's and get the same number every time, then you have a first degree function. What happens if we have some higher degree functions? Well, let's take a look. Our x's are evenly spaced. They're not going by ones, but that's okay. They're going by 0.1. So as long as the x's are evenly spaced, that's fine. Then let's subtract some y's. So we get 1. 3.92 minus 2.88 is 1.04. 5 minus 3.92 is 1.08. 6.12 minus 5 is 1.12. And then finally, we get 1.16. So this function is definitely not linear, right? Because our slopes are not the same. So this we would call D sub 1 for our first differences. If we know the function's not linear, now what we're going to do is subtract again. So let's subtract these pairs of values. 1.04 minus 1 is 0.04. 1.08 minus 1.04 is 0.04. 1.12 minus 1.08 is 0.04. And then the last one we get 0.04. So if you notice, if all of these differences are all the same number, that means this function has a degree of 2. And that's a 2. And that makes it quadratic, because all of our second differences were the same. Let's try another one. All right, so negative 5 minus negative 57.5 is actually 50. Oh my gosh, this stylus, 52.5. All right. Negative 2.5 minus negative 5 is actually positive 2.5. 25 minus negative 2.5 is, 27.5. Boy, I'm hoping I'm doing my math right. I'm doing this in my head here. 152.5 minus 25 is 127.5. All right. And then 455 minus 152.5, what is that? 302.5. All right. So obviously this function is not linear. So first degree is out. All right, let's do second degree. 2.5 minus 52.5, that's negative 50. Okay, now we get positive 25. Here we get 100. And here, let's see, 302.5. Let's see, that would be 300 minus 125, so 175. Okay. All right, so D2, not correct. So not linear, not quadratic. Okay, so not linear, not quadratic. Let's go to D3, see what happens. 25 minus negative 50 is 75. 100 minus 25 is 75. 175 minus 100 is 75. And if we keep going, it's going to keep staying at a constant of 75, which means this function has a degree of 3 and it is cubic. So you just keep subtracting until you end up with a line of differences that are all the same, and then that tells you what the degree of the function is. All right, we're moving into section 6.2. So we're going to find the volume of a rectangular prism that started as a cube and got modified a little bit. So imagine a cube. When you have a cube, all the sides are the same length. I'm going to call them all x. Now suppose we take the height of the cube and increase it by 2, and then the width increased by 3, and the length gets increased by 4. What would be the new volume of this final shape, which is no longer a cube? It's technically a rectangular prism, but we won't get into semantics. So the volume of the initial cube, our first volume, is x cubed. We'll call this 0 for initial volume. But our final volume would be this. So our x cubed is the same as x times x times x, which represent our length, our width, and our height. So our new height is instead of being x, our new height is going to be x plus 2. Our new width is going to be x plus 3, because it's the initial x plus 3 more. And then our final length would be the initial x plus 4 more, so x plus 4. All right, this form that we've just written our new volume in, this is called factored form. And the reason it's called factored form is because it's written as a product of factors, x plus 2 times x plus 3 times x plus 4. If we wanted to write this in expanded form, I'm going to erase this, give myself a little bit of space here. Let's see if it'll let me move these up. I don't know if it's going to let me. Nope, it's going to, that's okay. All right, well, I will try to write small here. So we have, if I multiply these two binomials together, so I'm just going to distribute x times x times 3. So x squared plus 3x, and then 2 times x, 2 times 3, plus 2x plus 6 times x plus 4. To save space, I'm going to go ahead and clean up this first 4-term polynomial here and write it as x squared plus 5x plus 6 times x plus 4. Now I'm going to multiply these two together. So I'm going to start by taking my x squared times each of these terms. So x squared times x is x cubed. X squared times 4 is 4x squared. Then I do my 5x times each of these terms. 5x times x is 5x squared. 5x times 4 is 20x. And finally, I do my 6 times each of these terms, plus 6x plus 24. And if I combine my like terms, I get x cubed plus 9x squared plus 26x plus 24. Sorry, that doesn't look like a 2. And this type of format here, this would be called expanded form. When you multiply everything out, you end up with what's called expanded form. Factored form is a product of factors. Expanded form means everything's been distributed out and you just have what we would look at as like a traditional general form for a polynomial. All right, we are going to figure out how to write functions for each of these graphs. So in our last example, we had 3 factors, x plus 2, x plus 3, x plus 4. When you're going from a graph to a polynomial, you want to start by looking at the zeros, the x-intercepts. Where does the graph cross the x-axis? These values where the graph crosses the x-axis actually give you your factors. So for this function, we would have y equals, I'm going to leave some space for a second, and I'm going to put, so here's the thing. If our root is negative 2.5, then our factor is x plus 2.5, and I'll explain why in a minute. If our root is 3.2, our factor is x minus 3.2. If our root is 7.5, our factor is x minus 7.5. Now, there could be a dilation factor, and we're going to call that a. So a is going to represent any scaling factor that might be applied to this polynomial. And how do we find a? That's where this extra point comes in. Any point on the graph will work, but the easiest one to use is the y-intercept. So let's go ahead and just plug this in, and then I'll kind of recap. So our y-intercept, remember, this is an x, this is a y. That means that when x is 0, y is 240. So if we replace our y with a 240 and replace all of our x's with zeros, we get 0 plus 2.5, 0 minus 3.2, and 0 minus 0.75, or 7.5. If I multiply, I'm going to grab my calculator here. If I multiply those three numbers together, so if I do 2.5 times negative 3.2 times negative 7.5, I end up with positive 60. Isn't that nice? So I get 240 equals 60a. Divide both sides by 60, and I get a equals 4. So my final equation is 4 times x plus 2.5 times x minus 3.2 times x minus 7.5. And it didn't say I had to write an expanded form, so we're just going to keep it in factored form. But I want you to make a connection here. I want you to notice that if the root is negative 2.5, then the factor is x plus 2.5. Now, why do you change the sign? Because remember, if these are x-intercepts, so because these are x-intercepts, that means our y value is 0 when we hit any of these points. In order for y to be 0, the factor has to equal 0. And if you set this factor equal to 0, what do you get? Oh my goodness, you get x equals negative 2.5, which is the root. So your roots, or your x-intercepts, relate to your factors in that the sign gets changed. So if the root is negative 2.5, your factor is x plus 2.5. All right, let's take a look at this one. So we have here same three x-intercepts. So I'm going to start with the same general format. So I have x plus 2.5, x minus 3.2, and x minus 7.5. All right, so everything seems normal, except I still need to solve for a, my dilation or scaling factor. How do I do that? Again, I'm going to look at my y-intercept, and I'm going to replace my x with 0 and my y with negative 90. So I replace that, and then I get times 2.5 times negative 3.2 times negative 7.5. We've already done this. We already know that this equals 60. Divide both sides by 60. And we end up with a equals negative 3 halves. That's a halves there. So we end up with y equals negative 3 halves times x plus 2.5 times x minus 3.2 times x minus 7.5. All right, so in general, if you have to write a cubic function, what are you going to do? You're going to look at your x-intercepts, and you're going to convert them to factors. So step 1, take a look at your x-intercepts, convert them to factors. Step 2, you're going to find your scaling factor. Use the y-intercept. Whoops, forgot the hyphen, that's okay. Use the y-intercept to find A, which we can call our dilation factor or our scaling factor. And there's that. Kind of messy, but that's okay. All right, we're going to do something similar now. Use the graph of each function to determine its factored form. Y equals x squared minus x minus 2. I know you can factor this. Like most of us can factor a quadratic trinomial without too much trouble, especially since the leading coefficient is 1. Everyone is probably thinking of the factors in their heads. Some of you might even be able to go ahead and factor this letter b, which is a 4-term cubic function. So some of you might be able to factor it, some of you might not. But what we're going to do today, instead of factoring algebraically, is we are going to look at the graph and let the graph determine the factors. So I'm going to go ahead and switch to Desmos, and we're going to take a look at x squared minus x minus 2. So I have x squared minus x minus 2 graphed right here. And if you look, we have two x-intercepts. So I have one at -1, 0, and I have another one at 2, 0. So we're going to relate our x-intercepts to our factors. Remember, if the x-intercept is at x equals -1, the factor would be x plus 1. If the x-intercept is at 2, the factor would be x minus 2. You change the sign. So based on our x-intercepts, so x-intercepts, we're at -1, 0 and 2, 0. So our factors are going to be x plus 1, x minus 2. For the next one, I'm going to turn this graph off and turn on my 4x cubed, come on, plus 8x squared minus 36x minus 72. And I might zoom out just a little bit so you can see this a little better. It's going to get too skinny. That's all right. Okay, so we've got this lovely cubic function, and we need to find the x-intercept. So in Desmos, I'm just going to click just to make sure that really is at -3, and it is. So we have -3, -2, and +3. So when I go back, so if my x-intercepts are -3, 0, -2, 0, and +3, 0, my factors would be x plus 3, x plus 2, and x minus 3, because my intercepts were at -3, -2, and +3. I need a dilation factor. I'm going to give you a little gift here. If you have the function written in expanded form or general form, the number that is what's called your leading coefficient, it's the number that is the coefficient of the term with the highest exponent, is going to be the same as your dilation factor in factored form. So this number, you could just write right here. If you have any concern about it, all you have to do is go ahead and set all your x's equal to 0. You'd have to find your y-intercept. Where's our y-intercept? Our y-intercept is way down here. I need to zoom out a lot in a little bit. So somewhere in here, there we go. Our y-intercept is -0, -72. So if you solved for it by hand, -72 equals a times 3 times 2 times -3. So -18a. When you divide both sides by -18, what do you get? You get a equals 4. It's amazing. Okay, so anyway, just to show you a little shortcut, if you have the function already in expanded form, that leading coefficient will be the same as the leading coefficient, the dilation factor here. You can just bring it down. All right, and this is just kind of showing you how the factors relate. So remember, if your factor is x plus 1, it means you have an x-intercept at x equals -1, or the point -1, 0. And then same thing here, this would be at the point -2, 0. So how do your factors relate to your intercepts? They are, those roots or x-intercepts generate the factors, but it feels like you're changing the sign. So -1, 0 goes to x plus 1, -2, 0 goes to x minus 2. And then here's something similar with the 3 factors for the cubic. And then, of course, this number just comes down. One more, and then we have a little bit of review, and then we are done for the day. This is the longest lesson we're going to do in this whole chapter just because it was a double lesson. So I apologize that it's long, but that we'll get through it quick. All right, so last graph, go into Desmos. I'm going to make it a little bigger again so you can see those x-intercepts. All right, so it looks like we have an x-intercept at -1, 2, and 3. So since our x-intercepts are at -1, 2, and 3, we're going to have f of x equals x plus 1, x minus 2, x minus 3. Now, I'm not going to put an a in front because I have no a. My leading coefficient is 1, so my leading coefficient is going to stay as 1. So just to write it in factored form, if there was a number here, it would come down here, but there's an invisible number 1, but that's okay. So we just translate that down as a 1. So our final answer would just be this: x plus 1, x minus 2, x minus 3. And it says find the zeros, so I'm just going to write the zeros. So the zeros would be x equals -1, 2, and 3. All right. Quick mention, no example here, just a quick mention, and we will get more into this as the chapter continues, but we don't have to have actual x-intercepts to have a polynomial. So for example, this function right here has 2 roots, but they are not real. These are complex roots, which means they're going to have imaginary numbers in them because this function never intersects the x-axis. It's a quadratic. You can solve using the quadratic formula. You will get 2 answers, but they won't be real. They'll be imaginary or complex. And you can see that because we have a parabola, but it never intersects the x-axis. So we have no x-intercepts, but we do have 2 complex roots. Here, we have 2 x-intercepts, so we have 2 real roots. So by the way, if you hear zeros or roots, zeros and roots are the same thing. Zeros just mean the x values that cause y to equal 0. So anyway, so we have 2 real zeros. They're not integers, so again, the quadratic formula might be the best way to find those. And then, of course, if you have 2 x-intercepts and they lie on integers, like this and this, the fastest way to write your polynomial is, or to find those integers, is just a factor, right? Factoring is usually faster than quadratic formula. All right, quick summary, and we're done. So without graphing, number 1, find the x and y intercepts. Our x-intercepts, I'm going to write them as ordered pairs. So we would have x equals 2, so we would have 2, 0, then -1, 0, and then 3, 0. All I'm doing is taking the factors and changing these numbers. So 3 x-intercepts. Our y-intercept, in order to find it, you set your x equal to 0, so you get -4 times -2 times 1 times -3, which ends up being -24. So our y-intercept would be the point 0, -24. All right, to convert the polynomial to general form, you just need to expand it, which expanding just means multiply it out. X plus 1, x minus 5. So the first thing I'm going to do is go ahead and distribute this x into here. So what do we get? We get negative x squared minus x, and this whole thing times x minus 5. Now I'm going to multiply this guy by these two. So negative x cubed plus 5x squared, and then this guy by these two, minus x squared plus 5x. So my final answer would be negative x cubed plus 4x squared plus 5x. So I got to rewrite my y's. All right, so that's my polynomial in general form. The very last one, I'm going to erase this just to focus on actually, I'm going to go ahead and make a new page. So y equals x minus 1 times x plus 2 squared. So x minus 1 times x plus 2 squared. So I have y equals x minus 1 times x plus 2 squared. So the first question is, how many roots does this have? Well, technically, this has a root or an x-intercept at 1, 0, 1, 0, and negative 2, 0. So it has, therefore, 2 roots. However, it's not a quadratic. How do we know it's not a quadratic? Because we have an x times an x, but this x is being squared. So this is actually a cubic function with only 2 roots. How can you have a cubic with only 2 roots? Because this root is repeated. When a root is repeated, we say it has a multiplicity of whatever the exponent is. Multiplicity of 2. So it's the same root twice. If you rewrote this polynomial in fact fully factored form, you could write it like this, right? That x plus 2 quantity squared. So you'd have a root at 1, a root at negative 2, and the root at negative 2 again. What does that do to the graph? So if we have a root at 1 and we have a root at negative 2, and we have a positive leading coefficient. So here's what happens. When you have a root that has what's called an odd multiplicity, like this guy has an invisible 1 here, that's an odd number, that means that the graph is just going to go right through that root. So it'll go right through the x-intercept and just keep on going. But when you have a root that's got an even multiplicity, like 2, it's going to touch the x-axis, but then it's going to go back down. It won't cut through the x-axis. It'll kind of hit that root and just kind of bounce off. So we end up with a graph that looks like this. So we have an odd multiplicity root, which is a first-degree root at x equals 1, and then we have an even multiplicity root, or a second-degree root, at x equals negative 2. And that's our lesson, guys. Have a wonderful day, and